Welcome to Astronomy Daily, your source for the latest developments in space and astronomy news. I'm Anna, and today we're exploring a universe of fascinating discoveries that are reshaping our understanding of the cosmos. On today's journey through the stars, we'll discover how the Vera Rubin Observatory might soon triple the number of known satellite galaxies orbiting our Milky Way, potentially revealing hundreds of previously hidden cosmic neighbors. We'll also examine surprising evidence that suggests the sun itself may be creating water on the lunar surface, making this vital resource more accessible for future moon missions than we ever thought possible. Then, we'll look at the most precise timepieces ever launched into space as the atomic clock Ensemble finds its new home aboard the International Space Station. For stargazers, we have tips on viewing the dazzling Sirius this spring as it puts on a spectacular light show with prismatic colors near the horizon. And finally, we'll uncover why meteor showers can be so unpredictable, with new research suggesting our sun's wobble plays a crucial role in how these celestial light shows appear in our night sky. Let's get things underway. Our galaxy, the Milky Way, is surrounded by a family of smaller satellite galaxies, with the Large and Small Magellanic Clouds being the most famous members of this cosmic entourage. Currently, astronomers have identified about 30 of these satellite galaxies, but exciting new research suggests we're just seeing the tip of the celestial iceberg. The Vera Rubin Observatory, with its powerful legacy survey of space and time, LSST, is poised to dramatically expand our catalog of these galactic companions. According to a recent study, this observatory could potentially detect between 89 and 119 satellite galaxies when it begins its survey operations in a few months, effectively tripling our current census. Researchers reached this conclusion by creating sophisticated simulations based on data from the LSST Dark Energy Science Collaboration. They injected stellar population data into simulated surveys and tested the observatory's ability to recover and identify these faint galactic structures. These satellite galaxies are far more than just interesting cosmic neighbors. They're crucial to understanding how galaxies form and evolve. In the standard cosmological model featuring cold dark matter, galaxies form as dark matter halos merge over time. The smallest and dimmest of these structures are ultra-faint dwarf galaxies, which represent the lowest mass dark matter halos that contain stars. Finding and studying these elusive objects gives astronomers a unique window into the fundamental processes that shaped our universe. Many of these satellites are so dim and distant that they've evaded detection with current technology. The Vera Rubin Observatory, with its 8.4-meter primary mirror and revolutionary 3.2 gigapixel camera, will have the sensitivity to spot these cosmic lightweights. What makes this potential discovery particularly exciting is that the observatory is expected to find satellites at greater distances from the Milky Way, with lower luminosities and fainter surface brightness than we've been able to detect before, essentially revealing an entirely new population of galactic companions that have remained hidden in the cosmic shadows. The research behind these predictions is fascinating in its methodology. Scientists employed a clever technique where they injected simulated stars with specific properties into existing catalog data, essentially creating a controlled test environment. This scientific sleight of hand allowed them to precisely measure how well the Vera Rubin Observatory will be able to detect individual stars within these distant satellite galaxies. One of the key challenges in this detection process is something astronomers call star-galaxy separation. When observing such distant objects, it becomes increasingly difficult to distinguish between individual stars within satellite galaxies and the light from distant background galaxies that might contaminate the data. The researchers had to develop sophisticated techniques to address this critical issue. Their findings revealed that detection capability strongly depends on both the magnitude of the stars being observed and the half-light radius of their parent galaxy. For moderately compact stellar systems, their detection method proved 50% efficient at successfully identifying dwarf galaxies out to approximately 800,000 light-years from the sun. What's particularly exciting about these upcoming discoveries is that they'll help resolve several important questions in cosmology. Current observations of satellite galaxies match well with predictions from cold dark matter models, but theorists have long suspected our census is woefully incomplete. The new observations will put these models to the test. Moreover, many of the ultra-faint compact stellar systems already discovered have unclear origins. Are they star clusters that formed in dwarf galaxies that were later disrupted? Or do they represent an extension of the dwarf galaxy population into an even smaller and fainter regime? The wealth of new data from the LSST will help astronomers definitively answer these questions. As one researcher noted in the study, each newly discovered system increases our understanding of the Milky Way satellite population, providing opportunities for unique, fortuitous discoveries among the most extreme stellar systems. These findings will advance our understanding of galaxy formation thresholds, reionization processes, heavy element production, and even dark matter physics. Turning our attention to the moon now. Future moon astronauts may have access to more water than previously believed, according to groundbreaking research from NASA, suggesting the sun itself might be continuously replenishing water on the lunar surface. This remarkable finding could significantly impact future lunar exploration and potential habitation. The moon, unlike Earth, lacks a protective magnetic field, leaving its barren surface constantly bombarded by energetic particles from the sun, collectively known as the solar wind. Scientists have long theorized, based on computer models, that this solar wind might be creating the ingredients for water right on the lunar surface, but the actual process remained poorly understood. To investigate this phenomenon, NASA researchers led by planetary scientist Lee Sia-yo at the Goddard Space Flight Center conducted a meticulous laboratory experiment using authentic lunar material. The team worked with 2 regolith samples brought back to Earth by the Apollo 17 mission, one from a trench called Wessex Cleft and another from the rim of a young crater in South Massif. The research team first prepared these 50-year-old samples by baking them overnight in a vacuum furnace to remove any terrestrial water they might have absorbed since arriving on Earth. They then constructed a specialized apparatus that included a vacuum chamber and a tiny particle accelerator to recreate lunar conditions. This allowed them to bombard the samples with hydrogen ions for several days, precisely mimicking how the solar wind interacts with the moon's surface. It took a long time and many iterations to design the apparatus components and get them all to fit inside, explained Jason McLean, a research scientist who co-led the experiment. But it was worth it because once we eliminated all possible sources of contamination, we learned that this decades-old idea about the solar wind turns out to be true. The results were definitive. When analyzing how the sample's chemical composition changed over time, the researchers observed a clear drop in light signal at exactly the wavelength where water absorbs energy, near 3 microns in the infrared spectrum. This confirmed the formation of hydroxyl and water molecules directly resulting from the simulated solar wind interaction. What makes this discovery particularly exciting is that the process appears to be renewable. The solar wind continuously supplies hydrogen ions that, upon striking the lunar surface, capture electrons from lunar materials to become hydrogen atoms. These newly formed atoms then migrate through the dusty regolith and bond with oxygen, creating both hydroxyl and water molecules that can accumulate across the lunar surface, especially in permanently shadowed regions near the poles. The experiment revealed a fascinating cycle of water formation on the lunar surface. When the researchers heated their lunar samples to approximately 260 degrees Fahrenheit, 126 degrees Celsius, temperatures typical of the moon's day side when exposed to direct sunlight, they observed a significant decrease in the water-related molecules that had formed. This wasn't surprising, as intense heat would naturally cause these volatile compounds to break down or evaporate. But what happened next was truly remarkable. After heating the samples for 24 hours and then allowing them to cool for another day, the team once again exposed them to their simulated solar wind. The water-related signatures promptly reappeared in the lunar material. This cycle of depletion and replenishment suggests that the solar wind continuously renews small amounts of water on the moon's surface in an ongoing natural process. The findings, published in JGR Planets earlier this year, represent a significant advancement in our understanding of lunar chemistry and provide valuable insights for assessing the sustainability of water resources on our celestial neighbor. The Atomic Clock Ensemble in space, known by its acronym ACES, has just reached a major milestone in space-based precision science. This cutting-edge timekeeping facility developed by the European Space Agency has been successfully installed on the International Space Station, marking the beginning of an exciting new scientific mission. ACES made its journey to the ISS on April 21st, 2025, launching aboard a SpaceX Falcon 9 rocket from NASA's Kennedy Space Center in Florida. The payload was part of SpaceX's 32nd commercial resupply mission. Just 4 days later, the station's Canadian robotic arm carefully installed the facility on the Earth-facing side of ESA's Columbus laboratory, where it's set to operate for the next 30 months. What makes ACES truly remarkable is the precision of its timekeeping instruments. It carries the most accurate atomic clocks ever sent into space. The primary timepieces include Pharaoh, a cesium-based fountain clock developed by the French space agency CNES, and the Space Hydrogen Maser, built by Safran Timing Technologies in Switzerland. These extraordinary clocks don't work in isolation. They operate alongside sophisticated microwave and laser link systems that will deliver time measurements from orbit with unprecedented accuracy. This configuration allows ACES to establish what scientists call a network of clocks, comparing the most precise timepieces both on Earth and in space. The system was developed through a collaborative effort between ESA and European industry partners led by Airbus. This international cooperation has created a platform that will not only explore the fundamental nature of time, but also test Einstein's theory of general relativity and potentially help redefine the scientific standard of the second using next-generation optical clocks. The next major step for ACES is its first activation, which will establish communications with ground control. This will enable telemetry data to flow from ACES to Earth and allow engineers to send instructions back to the orbiting timepiece while stabilizing its thermal systems in preparation for full clock operations. I'm so excited and proud that our incredibly complex and hugely important project is now in space after many years of hard work, said Simon Weinberg, ACES project scientist at ESA. This is a major achievement for ESA and the science community, and I look forward to seeing the results. This is ESA's jewel in the crown on the International Space Station. With installation complete, ACES now faces a 6-month commissioning phase, during which engineers and scientists will calibrate the instruments, thoroughly test the time transfer links, and characterize the performance of the atomic clocks. This meticulous setup period is crucial to ensure the facility can deliver the extraordinary precision it was designed for. During this commissioning period, ACES will connect with atomic clocks at selected ground stations several times daily as it orbits Earth on the International Space Station. The system's capabilities are truly remarkable. When multiple ground-based clocks fall within the same field of view for the station, such as 2 located within Europe, ACES can achieve a precision of 1 part in 10 to the power of -17, or about 10 quintillionths of a second, within just a few days. This level of precision significantly outperforms today's systems using navigation satellites like GPS by between 1 and 2 orders of magnitude. Even more impressive is ACES's ability to compare distant clocks across continents, something never directly accomplished at this level of accuracy before. These intercontinental comparisons will take approximately a week to complete. Once the commissioning phase concludes and the optimal operating parameters for Pharaoh are defined, ACES will transition into its 2-year science phase. This phase consists of 10 planned sessions, each spanning 25 days of intensive data collection. The ACES science team will validate all results before sharing them with the global scientific community. Now is an excellent time to view Sirius, the brightest star in our night sky, as it puts on a spectacular light show for evening stargazers. While most of us associate Sirius with winter skies, it's actually during these northern hemisphere spring evenings that this dazzling stellar jewel delivers its most impressive performance. Sirius outshines all other stars visible from Earth, appearing more than twice as bright as Canopus, its nearest competitor. With a magnitude of -1.45, Sirius is one of only 4 stars visible from Earth with a negative magnitude, making it 9 times more brilliant than a standard first magnitude star. This exceptional brightness can be attributed to its relative proximity. At just 8.6 light-years away, Sirius is the 5th nearest star to our solar system. The name Sirius itself appears to derive from the Greek word for sparkling or scorching, a fitting description for this brilliant white star with its distinctive tinge of blue. But what makes Sirius truly remarkable this time of year is its captivating scintillation effect when viewed near the horizon. As Sirius sinks toward the west-southwest horizon in the early evening, its light must travel through a much thicker layer of Earth's atmosphere than when it's higher in the sky. Our atmosphere, especially near the horizon, can be particularly turbulent, causing the starlight to refract and disperse. For bright stars like Sirius, this atmospheric turbulence creates a mesmerizing display of prismatic colors. No star rivals Sirius in this spectacular light show. When observed low in the sky, Sirius appears to twinkle vigorously, seemingly splintering into a dazzling array of colors, from ruby red to sapphire blue, emerald green to amethyst purple. The effect is so pronounced that casual observers might mistake it for a distant aircraft, drone, or even a UFO. To witness this celestial spectacle at its best, find a location with a clear, unobstructed view of the west-southwest horizon. The most dramatic effects occur when Sirius is just 5 degrees above the horizon, about half the width of your fist held at arm's length. Using binoculars or a telescope at low power can enhance the view, making those smoldering colors even more striking. After early May, Sirius will rapidly descend into the sunset glow and disappear from evening visibility around May 11th. It will remain out of sight for about 3 months before reappearing in the dawn twilight of mid-August, heralding the approach of the colder nights that lie ahead. Time now to solve a mystery. New research has shed light on a cosmic mystery that has long puzzled astronomers. Why are meteor showers so unpredictable? While casual stargazers might be familiar with reliable annual displays like the Perseids in August or the Geminids in December, scientists have actually identified approximately 500 distinct meteor showers throughout Earth's year. Many of these displays seem to appear and disappear with little warning, and now we may finally understand why. The answer, surprisingly, lies with our sun's subtle movements. Contrary to the simplified models we often see, our sun doesn't sit fixed at the center of the solar system. Instead, it wobbles slightly as it orbits around the solar system's barycenter, the common center of mass for all objects in our planetary neighborhood. Researchers Stuart Pelors and Peter Jeniskins from the SETI Institute discovered that this solar wobble dramatically affects the paths of meteoroid streams, the trails of dust and debris left behind by comets as they travel through our solar system. These streams of material can persist long after their parent comets have departed, sometimes lingering for centuries. When comets approach the sun, they warm up and release gas and dust particles that spread out into space. These particles form streams that orbit through the solar system, occasionally intersecting with Earth's path. But these intersections aren't constant or predictable without accounting for the sun's movement. The researchers found that the gravitational influence of the wobbling sun can either boost or break these meteoroid streams as they pass near it, similar to how spacecraft use gravitational slingshots around planets. This subtle gravitational dance causes the meteoroid streams to weave in and out of Earth's orbit over time. Computer simulations consistently failed to explain the movement of these streams until the researchers incorporated the sun's wobble into their calculations. Once they included this factor, the patterns of meteor shower appearances and disappearances finally made sense. The discovery explains why some meteor showers appear suddenly, dazzle observers for a brief period, and then vanish for decades before appearing again. It's all a cosmic choreography directed by the subtle gravitational influence of our wobbling sun. The most fascinating part of this discovery is the dramatic shift in orbital dynamics that occurs depending on a meteoroid's distance from the sun. When meteoroids are traveling beyond Jupiter's orbit, they're actually orbiting the solar system's barycenter rather than the sun itself. This barycenter, essentially the center of mass for our entire solar system, doesn't coincide with the center of the sun, but instead lies just outside it. However, once these meteoroid streams cross the threshold of Jupiter's orbit and move inward, the sun's immense gravitational pull takes over, shifting them from barycentric orbits to heliocentric ones, meaning they now orbit the sun directly. This transition creates what researchers describe as a step change in the motion of these streams. Pelors explained that this shift occurs twice during a comet's journey, first when approaching the inner solar system and the sun takes control, and again when departing as control returns to the barycenter. Each transition kicks the inclination and orbital node by a small but significant amount, altering the stream's path in ways that wouldn't be apparent if we incorrectly assumed the sun remained fixed at the center. Jupiter and Saturn play particularly important roles in this dance because their massive gravitational influence primarily determines the location of the solar system's barycenter. As these gas giants orbit Jupiter, completing a circuit every 12 years, and Saturn every 29, they pull the barycenter in different directions, causing the sun to wobble in response. This celestial mechanism explains why some meteor showers appear only at specific intervals. One shower that Jenniskins predicted and later observed in Spain occurs only every 60 years, precisely when Jupiter and Saturn align in positions that nudge a particular meteoroid stream across Earth's orbital path. The entire display lasted just 40 minutes, but produced a bright meteor every minute at its peak. Over longer time frames of millennia or more, these initially narrow streams gradually disperse. This happens because the stream stretches around the sun, with different meteoroids receiving gravitational kicks at slightly different times, creating a wider range of orbital motions within the stream and eventually resulting in the more predictable annual meteor showers we're familiar with today. And that concludes today's episode of Astronomy Daily. I'm Anna, your host, and I want to thank you for joining me on this cosmic journey through the latest discoveries in our universe. As I like to say, the cosmos never ceases to amaze us. I'd like to invite you to visit our website at astronomydaily.io, where you can catch up on all the latest space and astronomy news with our constantly updating newsfeed and listen to all our back episodes whenever you like. Subscribe to the podcast via your favorite podcasting platform, including Apple Podcasts, Spotify, and YouTube, to ensure you never miss an episode. We're bringing you the universe, one discovery at a time. Thanks for listening, and we'll see you next time on Astronomy Daily.